Hello, this is the third in this series of 8 short talks about introduction to flow frequency. I'm going to have a look at some of the statistical distributions that can be used for flood analysis. We'll look a little bit at a very commonly used distribution, the log Pearson type 3 distribution. We'll have a look at how different distributions work when applied to river flow in the Philippines, discuss the Weibull distribution, a different statistical distribution, and then some general comments about how important is the length of flow record to this sort of analysis and how parameters of distribution vary internationally across the globe. So, as we've seen before, we have river flow time series such as this one, some gaps in the data here, but we've got quite a long time series showing wet seasons, dry seasons as usual. And in this case, we are going to look again at the annual maximum data series, in other words, the highest flow event in each calendar year. Using the plotting formula that we've seen before in terms of rank order of those annual flood peaks, converted to a probability and a return period, we can generate a graph that looks like this. Discharge on the y-axis, a little bit compressed the numbers, but you can see it's a logarithmic scale. Probability along here, the median annual maximum flood here, the highest magnitude ones here and the lower magnitude ones at the left. And then on the top is the probability converted to a return period, the median being 2 years and the highest one for which there's data being about the 21-year event, because there are 21 years in the data series. In red, we've got the daily data, and then in blue is what happens if you average the data over 3 days, green 7 days, and in purple is a 30-day, a monthly average. And as you can see, as you average the data over longer time periods, the estimated discharge reduces because you're averaging with lower flow time periods alongside the high flow ones. This data has been fitted by a series of lines, and those lines follow the statistical distribution that is named the log Pearson type 3. Here's another example, and you've seen this example in the last lecture as well. This is annual maximum data from this site in the United States, and you can see that the 3 lines on here are labelled as log Pearson type 3, the blue one for the very recent data, the black for all data, and the orange for the slightly older data. Log Pearson type 3 is a statistical distribution, as we've said, which has proved very valuable for describing and analysing flood data. It's especially widely used in the United States, where it seems to fit a lot of the data extremely well. There are other distributions, and you will come across quite a lot of other names of distributions that have been used for different purposes, sometimes for floods, sometimes to look at distributions of all flows. Different distributions are sometimes used for looking at drought conditions as well. And some distributions tend to work better in some climate zones than others. And one of the things we need to do is to think about which are the most appropriate distributions for use in the Philippines. Why do we use statistical distributions? Well, we're interested in extreme values, and our data, as it shows here in the red circle, we don't have a lot of data in the area that we're most interested in. So if we can fit distributions to the data, we can then extend the data off to the high magnitude, low frequency events and start to predict how large these will be, if we know that these distributions fit the data well. The log Pearson type 3 data then as a distribution is widely used. Here's a typical data set published by Kitson et al. These are data from Thailand. Here are some annual maximum flood data. You can see the peak over 1,000 cubic meters a second, but there are some drier years in here. You plot can plot that on the graph, and you see that it has this sort of curved shape when plotted on this logarithmic axis, and this is also a logarithmic axis. It's been converted from 0 to 1,000 to a scale here that goes from 2 to 3, 3 being 1,000 cubic meters per second, 2 being 100. So on a log-log plot, we get this curved relationship. Individual flood events, a couple of them are highlighted to show that they fit the relationship quite well. Statistically, some different lines have been fitted. There's a solid line, which is the Gumbel extreme value distribution. We have a log normal distribution, which is dots, log Pearson type 3, all of which come in here. And then this other distribution here, which has been fitted. This is a straight line distribution, a power law relationship. And it's been fitted because of this very unusual event here, which is not in this record at all, but is what has been identified as a paleo flood, possibly related to a different climate condition, but also maybe just an extreme event. And the question was, how rare was that really extreme event? And you can see that in terms of the all of these distributions, all of which seem to work reasonably well here, that extreme event will be a very, very long way off the right-hand side of this plot. So it'll be a very, very unusual event. That's just an example of how you plot the data. The equation, and again, we don't need to worry too much about this, but the equation says that the log of discharge is equal to the mean of all of the log of all of your discharge values plus a constant k, a frequency factor, which is then multiplied by the standard deviation of the log of discharges. And the k value in turn depends upon a shape factor of the distribution, often referred to as c or c subscript s. Now, if you're going to fit this distribution, the computer packages that do this calculate the shape factor based upon the a histogram of the data, and there are uncertainties in this which depend upon the length of the flow record. As always, longer records are better, and short records do make it difficult to estimate the frequency of very large events. The question that this example gives us, though, is that it illustrates how do we extrapolate curves to look at rare events. This data set goes back to about 1950. How do we estimate the 1 in 100 year event from only 50 years of data? We have to extrapolate. We're going beyond the range of our data. And that's where distributions are really useful, but it's where we have to be very careful to make sure that we fitted the data very well and that we're looking carefully at how the distribution behaves, especially in the largest floods that we have on record. In the Philippines data set we're talking about and you're going to be using, two distributions have been fitted, the log Pearson type 3 and also a distribution called the Weibull distribution. They both work quite well in the Philippines, and actually we've found that some of them work better in certain parts of the Philippines and the other one in other parts. In our 3 data sets that Pammy will explain to you in a different presentation, we find in this data set, the SWS, that the log Pearson type 3 in 66 out of 184, about 1/3. In the BRS, it's 34 out of 179, so about 20% roughly. And in the Cagayan data set, it's 17 out of 49, so again, about 1/3. The remaining 2/3 or 80% in this data set are better fitted by the Weibull distribution. And we've plotted here in different colours, the green for Weibull and the orange for log Pearson type 3, which distribution fits the data better, and the circles are scaled by the size of the 10-year estimated flood. So you can see, for example, in the Cagayan, it's nearly all Weibull fits that are best, and in actual fact, for the rivers across the Philippines with the biggest floods, it tends to be the Weibull distribution that works best. An exception maybe being up here in northeastern Luzon, where the log Pearson type 3 works for the largest floods, and you can see that there are other regions where the log Pearson type 3 does give slightly better predictions. A typical example here for the Biaos River, we have the two distributions fitted to the same data set. Sorry, the vertical scales are slightly different, but you can see that the points, the red data are the daily flood magnitudes, the ones we're perhaps most interested in, and you can see that largely speaking the data are fitted well by the distribution. An issue here that the largest flood on record plots above the Weibull distribution. Here it plots exactly on the log Pearson type 3, and we are always interested in the largest floods on record. How important is it that this is slightly above the predictions, whereas for the log Pearson type 3 it's much closer? And that's something we could look at in a more detailed analysis of the data if we needed to. Many of the records that we've got in the Philippines are really quite short. They're only a few years long. How important is the length of the data record? Globally, most flow and rainfall records are only 30 to 50 years long, sometimes shorter, sometimes a bit longer, but a lot are quite short. And we know that short records and small data sets lead to higher statistical uncertainty. Short records are less likely to contain extreme values. Short records might, because of clustering, overrepresent extremes or underrepresent them. A lot of work has been carried out looking at the length of record, and a very detailed study on rainfall records was carried out by these two researchers in 2013, and they looked at 15,000 rainfall records globally with lengths anything from 40 to 163 years. Now, you don't really need to know the distribution that they were working with, but it's a generalized extreme value distribution, sometimes called von Mises distribution, quite a complicated looking equation. The key parameter in here is what's called the shape parameter. And here is a graph of the shape parameter against the length of record with confidence intervals, showing that if you only have a 10-year length of record, the estimate of the shape parameter, the mean, is 0.05, but the confidence interval goes from over 0.5 to minus 0.6. When you get to round about 50 years, the confidence interval's coming down, and increasing the length of record to 110 years doesn't bring the confidence interval down that much. And so they point out that once you get to certainly 70 years, the confidence intervals are getting reasonably low and certainly manageable. Once you get to about 20 years, the mean of this parameter has stabilized. So you can get a reasonable estimate of the mean at 20 to 30 years. You want to be going 50 to 70 years to get the confidence interval down. Longer than that is nice, but it doesn't make a lot of difference to these confidence intervals. Now, we don't often have 70 years of data. If we wait another 20 or 30 years, we'll get more and more records that are longer as time goes on. How do we manage that? Well, we have to, first of all, acknowledge the uncertainty and report the uncertainties in our estimates. But we can also compensate a little bit by analysing data from many locations together. Individual short records, when combined, can to some extent overcome the uncertainty that we have when analysing just a single record by giving us a pooled length of record that's much, much longer. Just want to say a little bit about shape parameters, because the shape parameters you will often see referred to, and they are important. This is a mapping from that same study of the shape parameter, blue being negative values, red being positive. And I think you can see from this that there are different parts of the world with different colours tending to dominate. As it says here, green colours in in the Philippines. We don't have much data from Philippines. But that's similar to Southeast Asia, Eastern Australia, much of the US, parts of Europe. Red colours we see in Central Europe, we see in Western Australia, we see in some West Coast areas of the US. And in the top graph here, we've plotted the effect of those shape parameters. Negative value is the green line, a small positive value is the blue, and a bigger positive value is the red. And this is rainfall on the x-axis and then probability on the y-axis. And the further down this line comes, these lines come, it implies there's more high magnitude events. More of the time the flow, or the rainfall in this case, is above 100 millimeters. And so the red with the high shape parameter value has more large events, significant in flood generation, than do the blue or the green. So the shape parameter affects the frequency of extreme events. The highest shape parameter value has the greatest probability of large events compared with the lower shape parameter values. So in the Philippines, we've got a greenish color here, implying slightly lower variability, lower frequency of extremes than we might get in certain other areas. Doesn't mean that extremes aren't still present in the Philippines, but they are the distributions have lower standard deviation. The distributions are less variable than when you have higher values of the shape parameter. Using those distributions, choosing which distributions to use for different purposes is actually quite a complicated exercise. We will, in the practical, you will be looking at some results from the Weibel and Log-Pearson type 3 distributions and trying to understand how you can use those to estimate different flood magnitudes. Thank you.